That should work, hopefully. And the share screen. And let's hope that Teams has a better day today. So can you see my screen? Does that work? Okay, so at least that should work. And I hope it's not frozen, so you see it moving, I guess. So at least that seems to be all right. Good. Yeah, maybe it's too early for Teams as well. Who knows? I don't understand all this technology. Maybe the little man in the computer needs a little bit of a break as well. I mean, it's hard work to do all these calculations and you know, all that stuff. God, I'm talking so much rubbish lately. Okay. So shall we make a start? Because what I want to do today is I want to start a new topic. I want to start with reaction kinetics. This is a topic that a lot of people find quite daunting, but I hope I can make it less scary. And I think most of you have done some kind of kinetics already. And the link to it with things is we've always said, you know, a reaction is fast. Protein folding is a very fast reaction. The exchange of proteins usually is very fast. But we need to define what is fast. And no, I'm not going to ask that in the test, which I will set you. I think I have sent out the list of topics that will come up, and if you look on it, kinetics is not on the test, so you are safe. This will be probably sometimes next term. Okay, yeah. So we need to talk a little bit about how fast reactions are, and this is also very closely linked to what we are going to do next term, at least those people who are doing the BI 301 enzymes and metabolism module, because this will be absolutely chock-a-block with reaction kinetics. We really need to get a solid understanding of how fast reactions actually work. And before we get started, I would like to do a little bit of terminology, but please don't forget to record your attendance in Moodle if you haven't done so. And I think if you scroll up in the chat, I was just about to say Bernardo has posted the Moodle link, but he has posted it again, so thank you very much. So first of all, let's do a little bit of terminology alert. When we talk about kinetics, we are talking about speed. That I don't mean the stuff that you take before you go into a nightclub. we are talking about velocity, and we are talking about rates. And so what are the differences between these things? How would you define speed? How would you define speed? What is speed? I know playing tennis against yourself and winning, some people would say that. It is, yep, I think that is a good definition. It is distance over time, or maybe probably better formulated, a change in location. Change in location per time change, or change in time. Let me put it like that. Change in time. And what is velocity then? Yeah, you could say displacement per change in time, pretty much the same. Velocity is also, you would usually change in, let's be more sort of general, change in something per change in time. And with speed, we probably can also be quite general and say change in something, because we can change not only the location where we are, but we can also change, for example, the amount of donuts that we can eat or something like that. Now, why would we have two different words for speed for the same thing, i.e. speed and velocity? And I think Charlotte and it is already mentioned it. Velocity has a direction. Velocity has a direction. Whereas speed has no direction. And that means a speed is always something positive. It's always positive. So I drove with, say, 30 miles per hour or something like that. That would be a speed. I can't drive a negative speed. On the other hand, when I talk about velocity, velocity can be both, because it has a direction. It can go either in this direction, or it can go in the opposite direction. So in this direction, we would say it's, for example, positive. In this direction, in the lower direction, it would be negative. So a velocity can be both positive or negative. And it can, of course, be zero. So what is rate? So we have a change, velocity change in something versus change in time. What is a rate? Change in something. Yep. Change per time. Okay. Yeah, you're right. Change per unit time. Yeah. Bernardo, I love your definition because rate is exactly that. It is a change in something. Change in something in one quantity. Let's write that down. Change in quantity divided by the change in another quantity. That sounds really, really abstract, but that's a very general uh, definition. For example, if I say donuts eaten by different people, that would be a rate. It doesn't necessarily have to have the word time in it. As long as there's a change in something divided by change in something else, we could define that as a rate. That's just a sort of a very general expression, and rates are also always directional. Directional. So it can be positive, or it can be negative, or it can be zero. Donuts consumed per bite. I would probably do it the other way round, maybe bites per donut. That would be a rate. Unless you can eat 2 donuts or 3 donuts or 4 donuts per bite, but that would imply that you have a rather big mouth, which is perfectly possible if the donuts are not too big. But so we are talking about speed, velocity, rates, and very often we just use these things interchangeably. But I just wanted to make sure that we are all really have a firm understanding what's what here. Now, when we're talking about reaction kinetics, we usually have a very simple reaction. So let's write down a very basic reaction. So for example, we have a component A, which reacts, and it forms component B. So that would be a very simple reaction. Very often you see this as A turns into B. Sometimes when we talk about enzymes, we would probably write substrate turns into a product, or sometimes you also see reactant. Reactant turns into also a product or something like that. So you would see very different ways of writing that, but they all mean the same thing. Okay? And we can define rates for these reactions. Rates for a reaction. But before I go into what is known as the general rate law, let's do a little sort of experiment where we talk about the average rate. Average rate versus the instantaneous rate. Instantaneous rate. And to do so, let's just simply do a little sort of thought experiment. Let's do a little bit of traveling. I've got my axes here. So let's say I want to travel from Canterbury to London. Okay. And I start at, say, 3 p.m. How far is it from Canterbury to London, roughly? Does anyone know? 46 miles. Okay. Oh, wow. That's very clear. That's very, very specific. Let's say 60 miles. I go with Haley's suggestion because that's a nice round number. So here the distance would be 60 miles. And let's say it takes us 2 hours. It can also be, well, it depends on where in London, obviously. And let's say it takes us 2 hours, so it would be from 3 p.m. to 5 p.m. And so let's see how we get there and what our speed. It's about an hour. Well, you know, that's quite challenging, especially when you set off at 3 p.m. I think it's, well, what would be my average speed if I say it's 60 miles average speed? What would that be with these things? 60 miles from 3 p.m. to 5 p.m. It would be 30 miles per hour. And the way you've done it is you basically said, I start here at 0. London is 60 miles away, so the difference between them would be 60 minus 0 miles divided by 5 p.m. minus 3 p.m. Yeah, this is how we can do the average speed. And exactly, Dartford is a little bit of a problem. Okay, now let's do the traveling. So from Canterbury, we go on the A2, and I will sort of comment what's happening during our journey. So we go on the A2. We have a pretty good run on the A2, on the M2. We hit the M2 near Faversham, and again, we drive quite nicely. And okay, so why is this blooming lorry in front of me? Is that guy asleep? What's happening here? Why, where is this guy going? Oh, Jesus Christ! If he was going any slower, he would driving backwards. So that's not good. Okay. What do you mean you need the toilet? Really? We are just hit a good run here. No yet. Oh, right. Okay, good. Let's go to the service station. Okay, that's good. Let's grab a coffee there and you can go to the toilet. And yeah, okay, good. Okay, everybody back in the car. We've spent enough time here at the service station. Let's look, it's a good run. We can move. Road is clear. Why is it so quiet in the car? Oh, shoot! I forgot the wife at the service station. Ah, damn it! I have to... Shall I turn around? Get her? Yeah, I better get her. Otherwise, I have to sleep in the shed again. So I have to drive back, get the wife, and thank God, it's good run. And oh, no, 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 no. Stand still. Oh, yeah, okay, good run. And finally, I've arrived. Excellent. So what you see here is the profile of our journey. In one case, we didn't, or in two cases, we didn't move. So here the journey had a speed of 0, where we didn't move, or velocity or rate of 0, where we didn't move. But in generally, we moved all right. Here, in this range here, we had a journey or rate or velocity that was even negative. A negative velocity because we had to go back for something. And what we can do now is, while we have the average rate, and I indicate that just simply with this here. So for the average rate, we just say we take the distance divided by the time span. That was our average rate. That was 60 divided by the 2. So that gives us 30 miles per hour. We probably never or hardly ever drove exactly at 30 miles per hour. How do we find actually the speed that we drove at this time point here? How do we find the speed at this time point? What we need to do in order to find this speed here is we basically produce the tangent of our speed at exactly this point. We define exactly, we need to find the gradient at this point. We can find the gradient at this point here. We can find the gradient at this point here. And how do we find the gradient? Well, we just simply say, instead of looking at the entire journey here, what we do in order to find the gradients, here we can find another gradient. We just take a little slice of the time. We take this small slice of the time and look at how far we actually have traveled in this time. So, for example, instead of 2 minutes, instead of 2 hours, we look at 10 minutes intervals. So for the overall average speed, we said we take the distance, and I indicate that with this Greek, with this triangle, which stands for difference in location divided by the difference in time. But this is really on a large scale. With the gradients, that's the delta exactly, yeah. It's capital delta, I should say. Capital delta, which is very often used to indicate a difference. Now, with this one here, I again look at a change in location and in time. But this time it's not the capital, it's not the overall thing, it is a much smaller time unit. So for example, let's say it's for 10 minutes here. And in order to indicate that I'm talking about not the whole thing, I use the lowercase delta, which is something like that. It looks like sort of a very strange snake. It's the lowercase delta, exactly. So this means it is the time traveled, it is the distance traveled in, let's say, for example, 10 minutes. Okay? And that gives me a more, immediate velocity, more immediate speed. But then I could say, right, that is still too, it's not precise enough because that is sort of the distance traveled over 10 minutes. Couldn't I do it smaller? Couldn't I do, for example, location, change in location over change in time? Distance traveled in 1 minute. Could do that. Gives me a much better understanding of the speed that I'm driving. Actually, why should we stop at 1 minute? Couldn't we do it, for example, distance traveled at 1 second? Obviously, it would not be very much, but it would give me a very good and very precise, actually, very precise speed at that time. So what I could do is I could use my curve and slice that into 1 second intervals, and for each interval that I have, I can get the gradient and get the distance traveled. We'd be here all day, exactly, yeah? So why do we stop at 1 second? Couldn't I do, instead of 1 second, couldn't I do it distance traveled in basically an infinitely small amount of time? Very small time difference. And the smaller I make that, of course, the distance traveled will get smaller and smaller and smaller. But in order to indicate that we've got something incredibly small, we are now writing this not any longer with Greek symbols. We are writing our rate. We are writing the rate, or the speed in this case, or velocity. We write this as a change, and this time we don't use the Greek lowercase d, we use just simply the normal lowercase d. We write this as d location divided by d time. And this d just means an incredibly small difference. This is the incredibly small difference. That is what this d indicates. The gradient at any point is given as d location divided by d time. And this d location over d time, that is really our what is called the instantaneous rate. Instantaneous rate. We can basically measure what is our speed for every millimicrosecond of our journey. And how would we get this instantaneous rate? And Reynolds exactly hit the nail. If we want to get this instantaneous rate, what we would need to do is we would need to do what is called differentiation. Differentiation. Have I spelled it correctly? Differentiation. Yes. So that would be of calculus. So we would find the derivative of an equation, which is not terribly difficult, but I know that a few people are already starting to hyperventilate. We are not going to do that. So you are pretty safe. We are not doing differentiation, but if you want to learn about calculus and these things, it's not terribly difficult. Trust me, it's not so bad. Now, let's go back to our reaction because we need to define a few things. So let's say we have a reaction where we use a substrate A, and this is obviously we use this compound A. It is consumed in this reaction. And we are looking exclusively at the consumption of A at the moment. We will change the point of view a little bit later. So we start with an let me put it this way. We start with a concentration of A. That's our starting point. And here we have time. And obviously, somehow, during the reaction, over the time, the amount of A in our solution, the concentration of A will go down because A is consumed. Does that make sense? And the brackets just simply indicate the concentration of A. And over time, it will disappear. Can it get negative? Can we have a negative concentration of A? can we get a negative concentration of A? What do you reckon? You're absolutely right. A negative concentration of something doesn't make sense. You probably can have that on the Starship Enterprise because in Star Trek, anything is possible. But in real life, you can't have a negative concentration. So once we've reached zero, that's it basically. That's all used up. And so we can't have zero. Now we can determine the speed of the reaction. We can determine the speed of the reaction at any point here with exactly the same thing that we've done before. We just choose a time interval, and we check how much of the substance has changed. So we form the gradient at that point here. So we measure, if you like, the instantaneous rate for the reaction. So how do we write this? Now we said for our rate, the rate, we can write this as, this time it is not a change in location, it is a change in the concentration of A per change in time. Okay? This would be the rate, how fast actually this reaction proceeds. So, and we would talk about that when we say change in concentration per time unit. And because we used the rate of D, it means, it indicates that the changes are incredibly small. Are incredibly small. Okay, that is what this writing indicates. So our rate, which we can write as dA over dt, what we see is, when we look at this scheme here, is the gradient at any point that we are looking at, is the gradient positive or negative? What do you think? Is the gradient positive or negative? Now the gradient, because the gradient goes down, the gradient therefore must be negative. So when we are talking about consumption, the reaction rate, the gradient is negative, and we indicate that in this case just simply by a negative sign. So that indicates, this indicates here that we have a negative gradient, and it indicates that we have a consumption. And we will soon see that if we have a production of something, then the gradient becomes positive and this negative turns into a positive sign. But let's stay with the consumption of A. We can also then say there is a certain proportionality factor in it, a certain constant, and let's abbreviate the constant with a K. So this here has the name of rate constant. And to make this equation complete, we multiply it by the concentration of A to the power of something that is called M, or whatever you want to call it. This guy here is called the rate order. And we will talk about these things, rate order and rate constant, in much more detail. So what we have got here, so this dA, this change in concentration of A over time, that is our rate, equals minus rate constant times the concentration of A to the power of M. And that is actually something that I want you to remember. Because this equation here is known as the general rate equation, or general rate law. Okay, so let's, and what this general rate law indicates, it is just simply a mathematical expression. It's a mathematical expression or mathematical equation describing the rate of a reaction. Just simply a mathematical way of describing how fast. Now let's try and disentangle this a little bit. And we've started already with that. So let's talk about this K. This is the rate constant. And for all intents and purposes, this constant is what it says on the tin. For most cases, we consider it as being a constant. It doesn't change much. If we don't change our conditions of the reaction, then this rate constant will stay pretty much constant. So K equals rate constant. Why is it called a K? Because much of that stuff was developed by German scientists in the 1900s. And in German, you write constant, instead of a C, you write it with a K. That's why you've got the K. The rate constant is always a positive number. It cannot be a negative number. A negative rate constant does not make sense. So whenever you get a negative number for a rate constant, you know that something is wrong. Don't confuse it. We still have the negative sign here that indicates the consumption, but K itself is always positive. Okay? And of course, we know that the rate constant, for some of you who have done it, is also linked to the temperature of a reaction. And I just simply write down the famous equation. Has anyone seen this equation before? No? Yes, indeed. This is the famous, what is called the Arrhenius equation. Arrhenius equation, which links basically the rate constant of a reaction with the temperature of a reaction. I'm not going into detail at that point. So if you haven't seen it, don't worry, don't panic. We may or may not discuss that a little bit further when the time is right. So we have a link between the rate constant and the temperature. What else have we got? We've got the concentration of A, obviously. That's this guy here. We don't need to worry too much about that in the first place. And we have this M. This M is the rate order. Rate order or order of the reaction. Order of the reaction. And this here, this rate order, this M, is just simply, again, a mathematical expression. Mathematical expression of how to describe, basically, this rate equation. It's, as I said, it's and it's really important. It's a mathematical expression. It doesn't tell you a lot of other things. It just makes this equation workable. Now, what can M be? M, this rate order, can be any number. Can be any. Now, with that, I mean any number. It can be whole number, so an integer. It can be positive. It can be a negative number. It can be a fraction. It can be an irrational number. It can be whatever you can think of. It is possible that M is this number because it is just simply a mathematical expression. I remember about 4 years ago, I had a discussion with a student whether M can also be an imaginary number, where you, for those of you who don't know what an imaginary number is, basically it is the solution to the equation square root of -1. That would give you an imaginary number. If m can be an imaginary number, I don't know. I don't know what it actually means, but it's certainly an interesting concept. But m can be any number, as I said. In contrast to m, we have what is called the molecularity of a reaction. And by that, molecularity of a reaction is defined as the number of molecules that interact with each other. Interact with each other in a certain step. So, molecularity of a reaction, this can be only whole numbers. So it could be one molecule doing something. It can be two. Can it be zero? Can the molecularity of a reaction, can it be zero? What do you think? You think absolutely right. No, it can't be zero. Because if no molecule is interacting, then there's no reaction. So molecularity of a reaction can only be a whole number, 1, 2. What about 3? Can it be 3? Can 3 molecules? Can the molecularity of a reaction be 3? Reynolds says yes. You're absolutely right. It can potentially be 3, although I think there is only one reaction that has been described in the literature so far where people could actually show that has a molecularity of 3. It's incredibly rare that it is 3. Most common are 1 and 2. It could theoretically be 4, but nobody has ever observed a molecularity of 4 in any process. So usually it is really 1 and 2, and 3 is extremely seldom. And it must be whole numbers for the molecularity because it tells you the number of molecules. You can't have half a molecule, right? It has to be a whole number for the molecularity of a reaction. On the other hand, when we are talking about M, the order of the reaction, again, let's have a look. Can it be 1? The order of a reaction, can it be 1? We are now talking just exclusively about M. Can it be 1? Yes. Can it be 2? Yes. Can it be 1.5? 1.5? Absolutely yes. Can it be negative 0.38. Absolutely. It can be anything because it is only a mathematical concept, right? So we have our rate law, rate expression, where we've got the rate of a reaction. And when we have a consumption, we have a negative sign here. We've got a rate constant. We have the concentration of what we are looking at. And we have a rate order. And this rate order can be basically any number. We will see a reaction where the rate order even changes during a reaction, which is particularly nasty to work with. But we have to. So this is really what I want you to understand from today's lesson. And I want you to be able to write this general rate equation and general rate law. Does that make sense? Are you happy with that? And tomorrow I will show you what we actually can do, how we can find out this rate order and also the rate constant from some. With that, I say thank you very much for watching, and I hope you learned at least a little bit of new stuff. See you tomorrow. Be good. Don't do anything I wouldn't do, and enjoy studying. Take care. Bye-bye.